Good morning, everyone. Welcome to, I think, I think it was last week. Not last week. Last lecture. I was about to say, welcome to the halfway point of graphics, but I think we're actually already past the halfway point of graphics. Or maybe the very beginning of this lecture is the halfway point of graphics. Because if my count is correct, it is 18 lectures. And if this is the start of lecture 10, then the halfway point is actually exactly halfway between lecture 9 and lecture 10. So, welcome to the halfway point of the course. It's also really kind of, when you think about it, a sort of a halfway point because we're going into flexibility week next week, which is a bit of a more relaxed week in terms of there not being any official lecture or tutorial content next week. So, those of you like Nix and Kai who are getting up with very, very small amounts of sleep because you're not necessarily in the same time zone that we are at the moment. Next Wednesday, you'll get a bit of a sleep in. Well, not a sleep in, just a natural amount of sleep. And you'll be able to relax there. I was talking to the people in comments earlier that I had baited everyone with the thumbnail for this video being myself photoshopped over my favorite character in Genshin Impact. And I was going to be playing that in the opening today. But Genshin only does a big update. I think it's about once every 4 weeks, once every month kind of thing. And it shuts down for about 4 or 5 hours during that time. And guess when that is? Lines up exactly with this lecture. So, so I didn't get to show off a bit of Genshin gameplay. But today, Clarissa said once every 6 weeks. Yeah, so I hit that window so precisely that I didn't even expect it to be possible. So I had to put my thumbnail up and everything like a couple of days ago. It was like, well. And it's quite interesting because what I was going to talk about today is about animation. Well, one of the things I'm talking about, modeling as well as animation. But I find Genshin to be a particularly good example of animation in terms of being able to use actually reasonably low quality in terms of 3D model characters. I don't want to say low quality, but low poly count. So not needing much surface detail and things like that, and very basic textures because it simulates a cell shaded anime kind of feel. So not a lot of detail, but incredibly good detail in motions and things like that. So it's really a lot about how the characters move that makes them interesting. So it's going to show like some of them when they're just standing still, they have like bits of fabric that are just sort of always swaying and things. So there's always interest and always like attention grabbing stuff. So just imagine from what I've told you there. I showed you something. I might try to log in at the end of the lecture because there's a chance that the the maintenance is finished by then, but I'm pretty sure it hasn't right now because I think it's only been going for an hour so far. It's usually minimum like 3 hours. But anyway, it's all right. I've got plenty of pictures in the lecture itself, so there's plenty of stuff to talk about. Okay, so what did we learn about last lecture? Last lecture we were doing a deep dive into design and art. I mean, I could call it a deep dive, or honestly, I could call it a very shallow dive, because all we were looking at there is an overview of it. I mean, I can't give you a definition of what art is in 2 hours, right? And instead, I tried to do it in one slide. But at least we got some big open questions, and we looked at them. Minimum, we want to look at those big open questions because some of those are very, very fundamental to the core of what drives computer graphics. So graphics and art, we were talking about those things. Then we looked at how games are created and how we could piece together ideas for a game. And we put together ideas for a very, very big game. Some kind of AAA monstrosity that would take, you know, I'm thinking 200-300 people 5 years to make. We would be built up with massive marketing hype. We would release chock full of bugs and not ready for actual release. And then people would say we'd be worth buying maybe a year after release, when a skeleton crew of what's left of the dev team finally manages to fix all the bugs that were created in the accelerated development schedule that we're in. Not saying that this is happening for every single game in existence right now, but I could quite easily say that it's happening for more games that are released than it is not happening. This kind of cycle appears to be the norm nowadays for big budget computer games. It's a bit awkward, but you know, this is the timeline we live in, so we're living in it. We also started to look at the art pipeline. So we looked at the idea of like, let's make one character, you know, and let's step through that process. I've repeated all those slides today. I'm going to go through some of them fast because we've seen them before, and then I'm going to go into the detail as we get to it. So what we're covering today is more detail on this art pipeline, but we're going to get back into what I would say is what a graphics programmer would be involved in, and also thinking about some of the tools that are used to create 3D art or 3D models and things like that, and where we would fit in there. Because there is a potential for a graphics programmer to be someone building the tools to support the artist, not necessarily just building the real-time engine to display this stuff. We might also be working on the code that is used in the beginning to even create the objects that end up in our scenes. So we're going to go into the detail. So the art pipeline, it's like we're glossing over the bits that the programmers are less likely to be involved in, like concepting and design. But when it gets to 3D modeling and rigging and animation, then we get much more involved. So going to go much closer into that, talking about how we might do these things. And you'll notice, like, the way I like to do this is that all I'm doing is piecing together some of what I would consider the building blocks, and these are things I've already taught you. So things like linear interpolation and scene graphs and things like that are things I've already taught you, and we're going to show how that all kind of pieces together to give us the ability to animate things. Okay, so continuing what we did on Monday, I would think the first 3 or 4 of these slides are ones we already covered. So we're talking about the process to go from the idea, something like a concept sketch, even before this concept sketch, the idea of a person. So we had idea of 2 people in that lecture. One was a technical person from a faster moving part of the planet, and the other was a primal person who is from like a pre-medieval era on the other side of the planet, and we were looking at how we might design both of them. So we have the ideas for both of them, but we don't have the concepts yet. So the concepts for this sketching, and then the design goes through all this process, and then officially pre-production, post-production. But we're going to break this up into more parts here. So I think we were talking about this. We didn't give them a name. And I think the question was like whether we even wanted to give them a name, because maybe we wanted to give them their own identity. But we looked at a bunch of examples, because a lot of things that we do at this point is do research. So we would look at humans in different ways. So we would probably look at like how people have represented robots over the years. Oh, that's right. The tech person was a robot. Yeah, so how people have represented robots in sci-fi and stuff like that. Is there anything we would take from that? How people would represent humans in a, was it like a primal age I was talking about it? Yeah. How that's been represented, how that might look. And we'd put together a set of references to say, these are all the different things that we could get, and we can take some inspiration from all these different things. We would never want to take something too directly. There's a lot of, there's a lot of value in learning from what other artists do, but we don't want to take exactly what they do. That's something that's, we take away our own creativity by doing that. I mean, sometimes it's just straight out plagiarism as well, so you probably don't want to do that. Having said that, heaps of art. We know heaps of art is very, very much remix of other art, and there are a lot of artists that will definitely say things like, there is nothing new. Like we can't necessarily say anything has been created new. Everything is a product of inspiration from other things. So that's okay. We can lean into that. But if you just like straight out copy paste, like for the what was it for the primal one? It was like straight out copy paste alloy from uh call it from Horizon Zero Dawn. I don't know if it's Aloy or Alloy because I haven't actually played the game yet, but it's on my list of things that I'm gonna do sometime in the distant future. But yeah, if we straight out copy paste that character, then it's a bit like, oh come on, we can do better than that, right? Anyway, we would then start drawing concept art, so there'd be lots of different images of this character, and we work from the references to build something up. Concepting, as I said, goes back and forth between probably an artistic director and the artists themselves. One example I saw when I was talking about it last time was it's Aloy. People are saying, okay, thank you very much. That's good. I'll try to remember that. What was I going to say? Yeah, sometimes this is a very, very involved process. So I think one of the examples that I had that I'd seen recently from Weta Workshop, not a digital character, but at this level, at a concepting level, doesn't necessarily matter whether it's digital or not yet. Something that has to be created. But one of the orc leaders, like one of the leaders of the Uruk-hai in Lord of the Rings, was they sculpted 100 different ideas for this character before settling on it and saying this is the captain of the Uruk-hai. So interesting. This can take a long time, and it's very important that this meets the vision of the game, because these characters, if you're looking at the main characters of the game, are going to have so much screen time, like more screen time than nearly any other thing that you're going to create for the game. So it's quite important that they capture the correct look and feel, and sometimes you want to make sure that they don't have distinct elements that people get hooked on and look strange, so you really need these things to work. Sculpting, I can't remember whether we talked about this last week. I think last lecture. I think this is where we got up to. So most likely this is going to be digital. Sculpting, I could put sculpting and modeling together in a sense, because sometimes you can go straight to 3D model in this case. There's lots of different ways to create a three-dimensional model that is then going to be used for other things. So you can sculpt it from clay and 3D scan it. People are definitely doing that. I think this happens a lot in the film industry when they make what's called maquettes for these. Jason's asking if we're going to go through a Blender modeling session. We're not going to, but I have pictures of it. For us to go through something like a Blender modeling session, I would have to actually learn Blender and know it. So in the work I've done in this kind of thing, I'm more likely to be the person sitting next to the person doing that. So I will be talking back and forth with them saying, this is what the engine looks like. This is whether the model worked in the engine or not, but I don't necessarily create the assets myself. I'm not entirely unique in that, but majority of the time, the coder's not necessarily the person making the model. So we're not going to go through this at that level of detail. I'm going to tell you a lot about it though. So if any of you are interested in picking up something like Blender, Blender's a free piece of software. I've given you some of the basic techniques, not enough for you to really know how to do it, but I'm going to cover some of the basic techniques today. Yeah, so more often a game asset would be, the entire process would be digital. So even the concepting, even the sketching might be done in a digital drawing app, not like Microsoft Paint, for example, but maybe like Illustrator or something like that. I'm gonna throw around a lot of program names today, but they're not super important because I think the idea of how to do things is more important than the individual piece of software that's used in the present day for it. I want the information I'm giving you to be like, you know, to last longer than the lifespan of just one particular program used to do something. At this point of sculpting, we're unlikely to say that this thing is game ready at this point. It's going to be raw geometry, which might mean that it has a whole lot of polygons because it's either sculpted or 3D scanned. I've got an example of that later, actually. And it might only be verts. It's going to be triangles as well, but it's not going to have textures or anything. It's not going to have animations, so it's going to be of limited use in a game scene, for example. Because I was talking about like in like a AAA game, and I was ballparking it here, but we'd have somewhere around 100,000, 200,000 triangles on screen. I've got an example of a model that's, I think it's 100,000 to 200,000 triangles on its own. So it's like a pre-optimized model, but I'll show you that in a second when I go into it in detail. So we would be working alongside artists at this point, where the programmer would be working on things like setting up the game world in order for in order for the assets to go in smoothly. And this is the point where we would probably have in our whatever source control we're using. It's not always Git, by the way. There's other source control that works quite well for large binary files like art files. 3D models tend to be just big chunks of data, and they tend to be awkward in that, when we use Git, we rely on only storing changes, so we can rebuild a file based on the changes moving through. Whereas for large binary files like 3D models, they tend to change like kind of the whole file at once. So your Git repo gets huge because the changes is like this 3 GB file changed between the last push and this push, and then the next push, this other like 10 GB environment file changed, and like your Git repo just gets really, really massive. So there's different ways of dealing with that. Git has a large file system set up that you can use, but anyway, it would be in a source control system. And one of the interesting things we would probably do at the beginning is the artist gives me a cube. And it's like, why do we need a cube? And it's like, the cube's actually vitally important because what we do is we set up the pipeline for the artist to give us assets. So instead of giving us a new asset that we have to incorporate into our system, they replace that cube with something. So the cube has the character's name, but it's just a cube. The nice thing about it, though, is we start working with that in the game world. So we can say, okay, this cube moves around at this speed. It is this size in the game world. And when it gets replaced by a model, the model ends up like, the same height as that particular cube. And so we don't have to do that much work when in our source control we check out one morning and the cube gets replaced by a model. And it's nice because then we'll send a message to the artist, go, hey, that looks really cool. And we knew we were ready for it because we'd already attached that cube to particular transforms to make it move around in the world and stuff like that. And when it comes in, it's the right scale. I think one of the funniest things I've seen when I was working with an artist once is we imported the model for the character into the scene and the cube disappeared. And I was like, whoa, what happened? We've lost the cube. Something happened in the last update and we have lost the model. So we don't have a character in our scene. And the artist was like, you sure? Because I definitely replaced the cube with the character. How come it's not in the world? And we're looking around at the world. So we've got like our plane that everything's moving around on, and where I expected the character. And it took us a little while, and then we looked up. And when we looked up, we were standing underneath this monstrosity, like 100-meter tall character. And we couldn't see it because we were in the space in between where its feet were. And it was so big, we didn't see it. And we were like, ooh, okay. So we had a scaling issue. The only problem was that the artist had changed the scale of it in between the original cube and when it finished. And they were like, oh, sorry. Okay. I'll put it back into the cube scale. We put it back in and everything was fine. But it's interesting like that. So you get this idea that we will we can start working on using the art assets before they even exist, which is kind of nice. Um, okay, so we had the sculpt 3D model kind of thing, and the next thing we might do is get this model ready, like game ready. So if it's been sculpted, if it's been 3D scanned or something, it may, as I said, have way too many polygons. So what we do was couple of options here. One option is we can build a model from scratch that uses the sculpt as inspiration. So we can say this sculpt is roughly this shape, which is actually not too easy to build upwards, like building polygons from primitive objects. The other thing we can do is sometimes an even automatic process to remove vertices from something. I actually have an image here of one like that. So this is, again, a lot of the time when I'm using examples, they're going to be famous examples. So this is the famous Stanford bunny, Stanford University. Are they called Stanford University? I don't know. Stanford University, Stanford College. I can't remember. In the US, this is a 3D scanned sculpture. So it's it's like a ceramic bunny that was 3D scanned, and you can kind of see how excessive the polygons are in this, because they've made it so that you can actually see all the individual polygons. So there's way more than we need here. So we're looking at this thing here. I don't know what the original scan was, but I'd say 300,000 verts here. It's unnecessary amount of verts for something that might be used in a game. And here we have a significant number of the vertices just simply removed from the model, and the approximation of them being made in much larger triangles. We can get away with this. It's not going to look like this like odd kind of polygonal object once we put textures and things on it. We can cover up the fact that there's a lot of like corners and hard edges on this thing. And if we want to really, really hyper optimize this thing because it's like just some kind of background object and we really don't want to be using our kind of rendering budget on this object, we could then cut more and more polys out of this and have it. I think I would nearly say this is too much. Like, we've optimized this thing too much here. It nearly doesn't look like a rabbit anymore. Like, something like this is what we could use in a modern game and get away with it. So that's the kind of optimization that we might do. I'm pretty sure this sequence here that was done by a user on Wikipedia was automated. So it shows you that you can just, grab a few polygons and just go, all right, make one out of these, which is just an average of all the other polys. The next thing we would do is we would UV map this model. So UV is the coordinates that we use for texturing. So the texels are on a UV axis. So we don't want to use X, Y, and Z for our textures, because our textures do not and never will exist in our world space or local coordinate space or anything like that. So we don't want to get mixed up and start thinking that texture coordinates are in the same system as our XYZs, and that's why textures are usually called UV coordinates. And our artist is going to talk about UV mapping being choosing which texture coordinates match which sections of the object. So they will go through a process to basically take, often for a model, a single 2D texture sheet. I showed you those before, I think way back when we were talking about textures. One of the Quake ones. So they'll take a 2D sheet and they fill that up with stuff and wrap that around the object, which means they will actually be the ones saying this vertex maps to this position in the texture. This vertex matches to this position in the texture, and do that for all the verts. There are ways to automate that. We don't necessarily go to each vert and type in the number. That's a little bit excessive. There's a lot of stuff today we're going to look at, like, all of this stuff is possible if you want to manually do it by hand and type a number in for every vertex attribute for every vert that you have. But most of what we're going to try to do is never treat vertices individually. Treat them in groups. Use processes to interpolate between them and that kind of thing. Because if we were to try to do everything manually, single vertices, so many of the games and movies and stuff that we know of would just never have happened, because they would have been taken so long and been so painstakingly exact in everything that they did that we just would never have gotten through developing any of them. But anyway, once we've done that, we know that our two-dimensional texture is mapped onto our object based on the UVs, the texture coordinates that are on the verts. The next thing we can do then is to paint the textures. So our artist will then look at the texture, which will then have an outline of the kind of objects and where it wraps around things, and they will start painting those textures. Different kinds of art styles are going to do this differently. So I showed you the Borderlands art style at one point, which is very much a comic-based art style. So they would look at any of the edges that that are on the object, and they will put harsh black lines there. And the other parts, they were using a watercolor style for most of it. Other games where you might get very, very realistic kind of games. So I was looking at like your maybe your Rockstar games, like your Red Dead Redemptions and stuff like that. They might actually be using photos of real horsehair, for example, to use it, and then stretching it and moving into the texture so that it works. A lot of modern games now for faces are using very, very high detailed multiple photographs of people's faces and then putting them in the game. I think was it Death Stranding was doing that. The first game to do that, I think, was LA Noire, where they had this really excessive face camera rig to do it. I mean, it's not the first game to do it, but it's the first game to do it in really, really exact detail. They wanted to capture human performances and put them straight into the game, rather than having their animators automate the process of people talking and things like that. So we would have all of those surface detail mapped onto the textures, and this is more than just textures, by the way. This is other surface detail. We call them materials sometimes. We call them maps as well, because, like, you know, we're mapping something to the UVs on the model. So this isn't just color. It's surface texture and things like that as well. But we're going to talk about that later, because we're going to talk about lighting, and then we're going to talk about how different surface texture affects lighting, because some surface materials might be shiny, other surface materials might be rough, things might have arbitrary corners and bumps and stuff in it. So if you've ever heard of bump mapping, specular maps, I don't know if you would have heard of specular maps necessarily, but we're going to go into those as we go on into lighting. But I'm going to teach you about lighting before I teach you about those. But anyway, at this point, this stuff will get added to our models. Yeah, so that's the polygon rendering there. The next bit, we're going to go into this bit in much more detail today, probably in the second half of the lecture, looking at the time. Rigging and animation. So we have a rudimentary idea of what animation is based on what I've taught you previously, and also last week's tutorial, because last week's tutorial we were animating, right? We were animating by adapting transformation matrices between objects and using the scene graph to animate objects relative to each other. When we start animating internally within an object, the system of just like modifying transforms is not necessarily going to help us that much, because there's not many separate transforms within an object unless you have a complicated multi-part object within the scene graph, which is possible. But the way we will often do it in things like character animation and stuff, like, not just characters though, lots of other things, we would have an internal bone system in the characters, which is attached to the mesh. So for the moment, everything we've been doing is thinking of the mesh as just the outer surface of an object. But if we take a system that's very similar to like a physical human, I have rigid bones inside a soft, fleshy covering. And so the mesh might actually deform and shift and change shape based on the bones underneath, which are rigid. I'm going to go into this in more detail, so I don't really need to say it all here. But this part of the process would probably happen at this point, after we've got our model maybe optimized maybe to this point here, and we've got textures and things like that. We would then rig the model. And so rigging has become, you know, a well understood term in 3D digital art and animation, that we need to attach a skeleton to a mesh, and then the skeleton is used to animate the mesh. And these animations will be an ongoing thing, because every time we do a design iteration in what we're creating, or a directing iteration in terms of film, because this film has less in terms of game designers and more in terms of artistic direction. That anytime that happens, we may go back and make new animations and stuff. And so we hit this point where we're iterating again. We're not necessarily like, because once we've done our concept art, we're unlikely to go back to it. So it's this kind of like, partly, in if we're talking engineering terms, it's partly a waterfall model, but also partly an iterative model. So when we're in rigging and animation, we're unlikely to re-rig a mesh. Like, the rig is probably going to be flexible enough when we first make it, but we're going to be iterating on the different animations we're going to be adding to a character. And so the question is, like, what ends up in the game? What ends up being what we receive if we go back to Break Time, which is the name of the game that we were making? What would we get as programmers? So as programmers, if this is assuming that we're not making the art ourselves, I know there's a lot of interest in that, because Jason's already asked today about a Blender modeling session. One day I'll learn it and I'll teach it to you. But what I've got so far is what I know about it and what I've read. So a lot of it is just like, oh, I had to read stuff in order to deliver this lecture, you know? So it's like, it's not really my field of expertise, but like, it's worth talking about. What I'm used to doing is just receiving stuff. So I would get a 3D model. The 3D model comes in basically as vertexes and index buffers. They won't be directly like that. I will basically get a whole buffer that then I will set up as a VBO, IBO, in the same way that we were doing with manually saying verts. Instead of us manually picking verts, we would take them from some kind of import tool. That's going to be in the tutorials this week. And it would have textures and other materials. They're kind of interchangeable terms, because a texture is also technically a material when you think about it from the artistic side. From the programming side, we will often not use the term materials as much, and we will separate them into their specific purposes. So we may get color textures, we may get normal maps, we may get bump maps, we may get specular maps, we may get even visibility maps, but we can often do that in the color texture as well. So little things like that. So we get multiple texture-like things that are two-dimensional things that are going to get wrapped around the objects, and we can get a set of animations. I will tell you more about what those animations are and how they work in the second half today. But from the moment, you know that these are the things you're going to receive. And then what we're going to do is like import these. And so we're going to have some way of taking all of this information and bringing it in and turning it into like basic numerical data that we can then use. So if it turns into basic numerical data, we can put it on the graphics card, and we can tell the graphics card to access bits of it at the right time to do things. So simplest idea of that is a vertex buffer and an index buffer. So we've seen both of those things. Vertex buffer being the actual points in the model, index buffer being which ones to use in sets of 3 if you're doing triangles. To do triangles. Most often we're going to be doing them in sets of 3 for triangles. So our job at this point as programmers would be bring these into the engine, make sure that all of this data is handled correctly, so that when someone says, okay, map the color texture to the UVs, we grab the correct texture. You can do some really, really interesting things when you map one of these other weird material textures as if it was a color, because then you'll get this kind of thing where the model is pure white where it was shiny, and pure black where it was textured and rough. And it's interesting, you can use that to view whether your shininess textures are working correctly and stuff like that. But in general, we want to map these to the correct parts of our rendering engine. We will then also do things like set up a transform for this model so that it gets the correct place in the world. So place being its orientation, its location, and its size, and things like that. And also we would be writing code to activate these animations, and not just activate the animations, but also make them work over the time frame they're supposed to work. So animations are going to come with a, so for example, simple things with the character is like, this is how the character walks. So the character has a walk cycle that lasts for 2 seconds, and it's repeated over and over and over again as it's walking through the world. So in its 2 seconds, it can put its left foot forward, and then its right foot forward, and then return to like the legs being next to each other. And if we just repeat that over and over again, we've got a walk cycle that's going to be used in our games. But we need to know exactly which frame of that cycle we're in a particular time, where the legs are supposed to be at that time. But we'll get into that later. Okay, so this is the interesting thing. How many artists was that in this pipeline? I've known people who did only one of these things. I've known other people who did many of these things. We call them generalists. But one of the interesting things in games are, and especially in film, more so in film than games, artists vastly outnumber programmers. So I reckon in games we're probably looking at about 3 or 4 to 1 artists to programmers. And in film, I don't know, like ballpark 10 to 1, maybe. I was trying to think of like Animalogic film company, because I actually knew a bit about it. When they're in the height of the Lego movie, they had around 400-500 artists and about 30 programmers. So we're looking at 10-ish, more than 10 to 1. So there's a lot of these people, and some of them might only be doing one of these jobs. So your concept artists might be highly proficient two-dimensional artists. There might also be people who literally don't use computers. They sketch on paper, and they bring all these sketches in, and people go, wow, this is so cool. You know, because these are the people who create from nothing. Sculptors goes back and forth between digital and traditional sculpting. So a lot of these people are working in clay and polymer resin and stuff like that. And they're building up the first three-dimensional ideas of the concept art. Your 3D modelers might be people who are then technical. So this is where we get into, like, from here, we can use traditional art. From here downwards, it's nearly all digital. Although texture artists and concept artists can often be the same people if they're painters. So if there's a crossover point, the concept artists can also do textures, but you're unlikely to get a really, really specialized concept artist who is also a rigger. Because riggers are there, like, I think riggers and animators are the most technical. Animators less so, but riggers 100% the super technical ones. They're the artists you hang around with and you go, you could have been a programmer, you know that. And often they actually do write code, because there's a lot of plugins for the art software that use Python and stuff like that. So these are the people who cross over the most into our world. Everyone loves the thumbnail for today. I apologize that I could not play Genshin in the actual lecture, because I hit the one time in 6 weeks for just a few hours that Genshin is down, and it's exactly while this lecture is on. Anyway, so 3D modelers might be the sculptors, but it's not always going to be the same, because we could have traditional sculptors here and then 3D modelers working with them to turn their sculpts into polygons. Texture artists, as I said before, are going to paint the surface that's going to be wrapped around the model itself. Riggers, it's kind of a mathematical process, rigging. I'll talk about it later. I keep saying I'm going to talk about it later, so you'll learn about this stuff later. The people that attach the vertices to theoretical bones that are the, like, if it's a creature, you can think of the bones being the skeleton inside the creature. But if it's other things, the bones can get much more abstract than that. And then the animators are the people that actually create the real-time movement of characters. And so this is a very, very interesting thing, because this crosses over with people who work with things like cartoons, cel-shaded animation and stuff like that. And bring out a lot of the life of characters, because you know your concept artist and your sculptors definitely bring out the life of the character, but the actual motion of it, once we get into real-time movement of things, is super important of how this works. This can really define a character, so you could have the same model for different characters. So if we took like a model which was like a skeleton or something, and we made it like shamble and stuff like that, then we're in a horror game. But if we make it do like this funny dance, then we're in like a comedic kind of game. But we could use the same model for that. So animate is quite important there. So yeah, there are so many specializations, so many different kind of different types of artists that might be working on these kinds of materials that we're thinking about of. Jason's asking if there are scene artists. Yes, there are as well. So I'm not sure where we would put that here, but definitely concept artists. Some concept artists might be doing a lot of character work. Other concept artists may specialize in other things. So some concept artists very, very much specialize in vehicles. So they will do all kinds of cars, spaceships, aeroplanes, and all this kind of stuff. So they're nearly like engineering drawing, technical drawing kind of people. Who's that person I was thinking of? Ralph McQuarrie, I think that's his name. Designed a great deal of things for the Star Wars universe. So most of those really iconic, very, very strange looking spaceships, I think, is Ralph McQuarrie. I'd have to look it up. I know Dan O'Bannon is another one who worked with James Cameron on a lot of his films. So the spaceships in Aliens and stuff like that was his stuff. So there's people that work not just in characters but also in other particular objects, and they might specialize. So concept artist is me putting a big grab bag around people who have their own specialties. So there's other people who might be landscape artists, and what they do is they just draw possible environments that people might want to work in and things. So it all comes from the idea of like what we did last week was we put together ideas. And so we said, ooh, there's a world that's technological, and then there's a world that's primal. And we'd get concept artists to draw scenes of those worlds. So I can already think of this dark, gritty, neon lit technological thing. And on the other side, I see blue sky, and I see a lot of greenery and sand and grass and trees and things. And so you get this kind of big kind of shift between perspectives when you go between these worlds. And our concept artists are the people we're going to rely on to give us the first images that we will then build up all this other stuff from. Sam saying I'm living in week 6 already. Oh, are you talking about my thumbnail or ideas of like visiting other worlds? Anyway, so it's huge, right? So this is like the overview of like what the art pipeline might be like. So now I want to go into detail on parts of this. So if we go, where's the overview of the whole pipeline? Oh, I don't have it here. Anyway, if we would go through each of these titles, we're going to jump in around where the 3D modelers end up. Oh, right. Sam, me saying last week. I always say last week for the previous lecture. It's like I go at a different speed than you, like I'm in a different part of the world. I must be closer to the black hole. Anyway, so we were not necessarily going to be talking about what happens with concept art and sculpting, but we're going to talk about 3D modeling and onwards here. So particularly today, 3D modeling, rigging, and animating. So the first thing we're going to look at is modeling. And there isn't just one way of doing this. There's actually lots of different ways of creating 3D models. So I've got the Stanford Bunny here. Stanford Bunny was done in one particular way, but we're going to look at 3 different possible ways of doing this that people use. There are other ways, but these are the 3 kind of, I don't know, most common ways of doing things. And also looking at the different ways that these are done is quite interesting because it'll show us different ideas about how models are actually created, enough that you'll have a wide range of things. So The simple way to think about it really is models are just a bunch of vertices. Um, More complicated, models are a bunch of triangles because vertices need to be ordered in order to make the triangles. But even if you just had verts and you had some program to automatically connect all these vertices together, you'll get you can get a 3D model out of this. You kind of want to make sure there's no gaps in it, no missing triangles or anything like that. But still, there are programs we can use to create a polygon mesh that maintains its shape as a polygon mesh, um, regardless of whether we push and pull things and stuff like that. It also comes with, as we said, textures, other maps, materials, things like that. Those are part of what we need to do to create a complete 3D model. So if we wanted to, we could say, I've just got 1,000 vertices. Place those 1,000 vertices wherever you want, and then make an index buffer to join them all up together. And so, yes, it's technically possible. It's technically possible to explicitly say what the coordinates in a local coordinate space that each vert should be at, and which verts it's connected to make triangles. We could do that. We could do that by hand. You have been doing that by hand, because nearly everything you've made so far, the simple rectangles and triangles and stuff you've made, is just type in the locations for these things, type in the IBO, and then you'll make triangles. We don't want to do this, because how many was I talking about? This thing had 300,000 verts. So if I said, okay, assignment 3, make a 3D model with at least 1,000 verts, you'd probably have to start now and start just typing in those numbers. And it would be the most boring and incredibly painstaking task you've ever done, because it would just be data entry, but then you'd have to keep reloading this model to see if it looked the right, it looked like it was going into the right shape, something like that. So this is obviously not something that we're going to do. So instead, what we're going to do is figure out ways that we're going to create multiple verts at once. And especially, these tools are going to be used by artists who don't necessarily get too deep into what even an IBO is. A vertex buffer they'd probably understand, but the idea of ordering the verts into triangles, they'd be like, well, the triangles need to just kind of exist, so we want to support the artists so that their creative vision and what they're doing doesn't require them to do a whole bunch of maths. So there's 3 techniques we're going to look at today. One's called box modeling, the other's digital sculpting. I put this one in quotes because like all of this is digital sculpting in a sense, which I did in the previous slides. I lumped all this together under sculpting. So yes, I'm going to call it digital sculpting, but it's another sort of hand wavy term. But people do tend to separate this from box modeling in a way, because it's slightly different workflow and slightly different software that's going to be used. And then also another one which is very interesting, which is 3D scanning and photogrammetry, which is the ability to create 3D models based on real-world models. We've definitely seen context for this with me talking about people sculpting statues and then scanning them in. So this is a way of doing things which can work really well. I had friends who used to do this kind of thing a lot, where they'd just be like, that's a cool rock. No, literally, they would say that. That's a cool rock. And then go and take 100 photos of this rock from different angles, put it into a piece of software that actually builds a 3D model out of it. I'm jumping ahead of myself. I'll talk about it when I actually get up to that slide. But yeah, a lot of stuff can be done with just using the real world. So box modeling is one of the simplest ways to do things. And it's kind of cool because you can start simple and you can slowly build up a model. And all you're going to do is start with a primitive object. So both of these started with a rectangular prism. You could start with a cube and then just start stretching it into this shape. And we do simple transforms, or we do partial transforms of part of the model. So what often happens is we'll take, so for this example, to make this bunny, so bunnies are in a lot of stuff today just because of the Stanford bunny. If we took this rectangular prism and we said, okay, I'm going to select the verts on this side and I'm going to scale them down. So it scales it down into the butt of the bunny here, so they're all closer together there, but the middle ones are still the same distance apart that they were. And the ones at the front we're also going to scale down a different amount. So what we're doing is we're moving some verts, but not all the verts at a time. And then here we go, okay, the tail needs more detail. We would just add vertices in between areas. So we could select a whole bunch of verts and say, I want more detail here. And what it would do is, usually the simplest thing we can do is we take a quad, because like at this point where we're doing mostly modeling with quads, but it would get broken down into triangles afterwards for rendering. We take 4 verts and we place one vert exactly in the middle of those 4 verts and create 4 more quads. And then we can take that middle vert and move it around. So we could drag it forwards or backwards, and that way we can start to sort of extrude objects out of other objects. So I used the term extrusion before when we were talking about creating the teapot by moving an object through space. We can do similar things here with box modeling, where if I wanted to, I could take this area here and add several verts there, and then pull the whole thing out and curve it and things. And that's kind of like the extrusion, because we would be taking this rectangular shape and dragging it through space like that. So the nice thing about this method is you start at a very, very low level of detail, and then you slowly add detail until you've got enough and you stop. So when we're trying to create a model with a low polygon count for high-speed rendering, so this is very much a game way of doing things, we would do this. And you can even see, like, this I think is a really good example. It's like, okay, how do we get a rectangular prism turn into a human face? And you'd be like, well, that seems like an excessive thing to do. But you can see the process here that they've done. So they've just gone, okay, let's go side on. We'll do a side on profile of the face. And then when we hit this point, we'll just extrude out both ways. And then we get the kind of width of the face. And then we start rounding all of our edges here. There's probably, considering these lines are curving, there's going to be more polys here than they've actually shown in this grid. But I think the grid is just so we can see what's going on here. And then as you go, you say, okay, these areas need more detail. So they've selected these areas around the eyes and the mouth and said, add a whole bunch of verts here. And then we start pushing and pulling these verts, forming them into roundish kind of shapes that we're going to use. So this allows us to go from simple objects to more complex objects, and it's a technique that allows you to stop at any point. So you can say, oh, I've got enough detail for this game, I'll stop at this point. Or it's like, no, we need this thing to be really, really detailed because it's going to be really close into the screen, so we'll spend more time on it, add more verts to it, add more detail. It is a manual process, though. It does take a lot of effort, and it's a process that is nothing like real sculpting, because you have more control over the medium than you expect. And your control over the medium is abstract and slightly mathematical. So this is a skill that must be learnt in a sense. It's not the same as a completely intuitive artistic process. It's like partially an engineering process. But anyway, this is often used in Maya, 3ds Max, Blender. I mean, Blender's going to appear in everything I'm talking about because it's an open source solution that tries to do everything that all of these other programs do. Another thing we might do is digital sculpting, and I like this GIF here. I found it on the Blender artists website. So this, instead of looking at vertices and polygons and things like that, approaches it from a much more organic perspective, where the first digital sculpting tools were made to allow clay sculptors to work in a digital manner. So people would use their tablets and pens, basically, and they would have a chunk of digital clay. And you can do things like add chunks of clay to this clay. And the idea that there are polygons and vertices in this is partially hidden. It is part of the process later on, but it's partially hidden while people are working on it. So you can just add chunks to things, or you can push things and carve things off, and the program will just deal with you doing that. So if I carve a section off a model, it will create new verts inside the model, new polys inside, and it'll make sure that it still looks good while I'm doing it. So there's a lot of work to do this in real time. A lot of the times, sculpting tools will use voxel technology as well. If you've heard of voxels, it's this idea of three-dimensional space being a pixelated space in a sense. I think one of the best examples of voxelizations, not exactly, is Minecraft. The smallest size, I guess, of terrain in Minecraft is a single block. But everywhere in the entire world in Minecraft, the blocks exist. So if you start digging, you don't find gaps in between. You don't have the surface and then nothing, the way we do in polygon rendering. If you take a block out, you see the other blocks that were kind of supporting it underneath. So if you start digging into the ground, you see other blocks there. Whereas if we're in a polygon rendered world and you were to dig through the top surface, the top layer of the ground that you're on, there's literally nothing underneath it, because the polygon rendering only worries about the outside edge or something. So when we're doing this kind of digital sculpting, hope you like the GIF. I think it's quite a good indication of how this sort of stuff works. You can see them making small changes. One thing that I like the most is you can see them copy pasting an ear in. So I guess ears must be a really, really annoying thing to sculpt. So they've copy pasted an ear from something else and then just sort of modified it for this character. Actually, I don't know if they did. There's a point where like a disc just gets attached to the side of the head and then it gets carved out. So yeah, this kind of process means if it's using voxel tech or it's just very advanced polygon rendering, this gives us the opportunity to basically like grab a surface and just kind of rub the surface until it goes smooth, or dig the surface with different kinds of tools. And a lot of the tools are going to be like named things like real world tools like scalpels and I can't remember like what the other tools are, but like, you know, like actual sculpting tools like different kinds of spatulas and whatever. I don't think they're actually called spatulas, but you know. I'm reaching the limit of what I actually know about this process. All I've done is watch other people do it. Yeah, and so the idea of this being made up of polygons and vertices is not a limiting factor in what we can create in these things. We will eventually, with this kind of sculpting process, need to say, all right, how many polygons did this actually end up being and how can we reduce it? But as we've seen, there's actually automated processes we can use to reduce these things. The primary tool people use for this is ZBrush, because I think that was the line of tools that first started using this technique. I don't know, but Blender also does it. There's others like Mudbox and things like that. So a lot of very highly detailed 3D modeling is done in these things, because you can see you can get this kind of more organic looking detail in this than you're necessarily going to get in this method. This method you can reach organic looking detail, but it might take a lot longer than just sculpting something like this. The third way we were talking about is 3D scanning and photogrammetry. So this is acquiring real world surface information using some kind of tool. So this is stuff I actually did. So this is one of my miniatures that I painted. This thing is an actual physical model. I won't bother getting it out. It's in the cupboard over there, but it's about 5 centimeters tall, and I painted it with just normal acrylic paints. And you can even see the block of balsa wood that I had it on when I took the photos for the photogrammetry. So laser scanners we can use. Often the use for a laser scanner is you put it in the middle of a room and it will scan the entire room. A lot of games that do kind of attempt at historic accuracy and things will use those. So for example, like the Assassin's Creed series, they had the Notre Dame. So this is an interesting story about when the Notre Dame burnt down. Well, it didn't burn down entirely, but a lot of it burnt. One of the most accurate representations they had of it was in Assassin's Creed, the game. So the Assassin's Creed developers gave all of their 3D files back to the Notre Dame Trust, so that when they rebuild the Notre Dame, they will have all of that information. They took all this, like, millimeter accurate laser scans of the internals of the cathedral so they can build it back the way it was. So it's really interesting that happened to have been saved by a computer game. We don't necessarily need to use these laser scanners. The laser scanners can be very, very expensive. You can actually get reasonably accurate, cheap results from photogrammetry. So, for example, this here, me getting this 3D model working from one of my miniatures was about 50 photos. So yes, that does take a while to take 50 photos, but it's not that long, and it definitely didn't cost me like I don't know how much laser scanners cost, but I think we're looking at, tens to hundreds of thousands of dollars for these things, for accurate laser scanners. So they're used for much bigger industrial purposes than just like making a model in a computer game. But the way that these things work is you can take lots of photos of an object, and based on what colors it sees in each of those photos, it will make a guess of what viewpoint each of the photos is looking at the model at, and it will be able to make a guess of the 3D geometry of the model. Let's jump across to this and have a quick look at this model. So you can see that this is most certainly a 3D model, where we're seeing in a perspective transform here. I could actually, I'm not sure if I even have this model anymore. Oh, you can see a hole in the head. There's a hole in the head where I didn't take enough photos from above on the model, so it wasn't able to build 3D data for this. You can actually see it underneath, so there's gaps under the model there and there where it had no information because I didn't take any photos from below. The gap in the balsa wood is actually me just cutting off the model at that point. But either way, what we have is very, very effective 3D geometry just from me spending half an hour taking photos of this thing and piecing them together in a particular program called Recap. So it's pretty cool. We can basically, I think that the amount of time and effort put into making this into a 3D model, it wasn't actually as much time as it would have taken someone else to model it. We'd have to count the amount of time I took painting it, but we've got a free texture here as well. So it's interesting that we can take photogrammetry and we can build up a 3D model. The only downside to something like photogrammetry is every single little curve in the model is going to have some intense density of triangles in it. I'll show you this because often we'll need to really need to reduce the polygons to make this work. So I'll switch to a wireframe of this model, and you can see it's like, wow, wireframes usually look like wires in a frame. But if I zoom in here, yeah, that's our triangle density. So this is just a tiny part of this model, and this is how many triangles we've got here. So what do we got? 124,000 vertices, 200,000 faces. So you remember I was saying ballpark figure for a real-time scene in a computer game might be about 200,000 triangles for the entire scene. We've used all of that budget up for this one miniature. And you can just see the density of the triangles here. Once I zoom out a bit, it's obviously excessive. It's obviously more triangles than we need. However, what we got out of it was this amazingly accurate rendering of the sculpt of this model just through photos. So no depth at all. So there has been no specific work done to collect distance to the camera. This is done purely based on the color information of the camera and the parallax differences of all the different shots that are taken. So super interesting. Not only do we get parallax, we get free texturing as well. So what we would do is probably bring this into another program and chop it up. So bring this into another program and do this to it. The cool thing about doing this is if we do this optimization to it, we do not lose our UV coordinates, because we'd have UV coordinates matching this to the texture that was captured in the photogrammetry. And then we'd have here the capability to maintain where those UVs are. So this thing would still look reasonably similar to what it does in its in its ultra high polygon state, we'd still get a decent look at it. I mean, there's sections of this here and stuff that are completely flat, and some of these blades are completely flat, and we'd hope that we could significantly reduce the number of polys there. I mean, the only thing that you can get out of this area being flat is that these triangles here are bigger and these are bigger. But otherwise, this is massive density in here, which is probably unnecessary. Right. Okay, we hit break time. And I want to talk about, this is like obviously because it's in the break slide, thinking about the joy there is in creating art. I highly recommend you partake in some kind of art, and it's not specific. It can be any kind of art that you want to, but I like to have something that takes me away from the idea of the day job. So there's something that you're going to be doing, which is like your kind of focus in life, and that's often going to be a job. It's often going to be something that drives you. For a lot of you at the moment, it's going to be, I want to do this degree, I want to complete it to a level that I'm satisfied with so that I can use it for something else later. For some people that's just going to be employment, but for other people it's going to be like, I want to do research or something, or I want to get into like specifically into a field I'm passionate about or something. I like to make sure that there's something else that I'm doing, something that will give me some relief from the day job, because the day job's often something that that asks a lot of us, and so it can build up a lot of stress and things. So having something on the outside, which is like, let's just do something completely different, I think is really nice. And especially, I think this is something that I was taught years ago, was like, do something that you can't lose at. So this is why certain hobbies, someone's coming to say hi, certain hobbies are a little bit dangerous, like competitive computer games, because if you're not winning all the time, it's not stress relief, it's just adding stress to your life. So for example, looking after a cat is very good stress relief. It's very, very hard. Well, got to remember to feed them all the time, but they give you a lot for what you give them. So I think it's nice. It gives you a break from the world. So for me, I paint little toys. So here's like some of the miniatures that I've painted. So there's a bunch of Warhammer stuff here. So this is like a 3D print of the Hulk, and just I can't remember what scale this is. It's like maybe a 1:10 scale bust of a fantasy dwarf kind of thing. And so like, I do this kind of thing and it helps me kind of wind down. It helps me like move my brain out of the constant struggle loops that I might be in a lot of the time. So I highly recommend getting into something like this. It can be anything you want, but art is a great one because it just allows your brain to create rather than work on things. So it's very nice. Sports and exercise and stuff like that are pretty good as well, because I think there's plenty of sports that you could play where winning or losing the particular game you're in is not really relevant. You're just having fun in doing it. Mike is saying time to look at my Instagram during break time. All of this stuff is on my Instagram, actually. So I have this other life aside from being a lecturer, where I am a an Instagram model painter. Haven't done it much recently. I've just been so busy. But anyway, let's go on break. It is 10 past 11 now. We'll come back at 11:15. And the second half of the lecture, I'm going to devote to rigging and animation, which is where I actually go back into a very much more technical side than a lot of the artistic stuff we've been talking about. All right, back soon. We're back. Still have still have a little friend with me. Um I tried to patch Genshin during the break, but it wasn't finished, and I don't know if it's even ready to run yet anyway, so let's not. It's super annoying because I had the slide all set up and I was like, oh, I'm gonna like open up Genshin and show you like all these little animation things that are really cool. But anyway, we'll look into that sometime in the future maybe. Okay, so let's talk about what animation is. I've made my images too high again. Let's see if that helps. Ah, there we go. So, we've talked about this already. I dropped that funny little bomb on everyone saying that no game that you've ever played, no film you've ever seen has ever had any motion in it. Not a single one of them. And I think that's an interesting way of looking at things, right? Animation is not motion. It's a series of still images that will create an illusion of motion because they're near enough to each other and they're played in a fast enough sequence that we ourselves, by our eyes and our psychological capability, will establish what's known as object permanence to things that are similar to each other. So, I mean, in the real world, we can think of this as like seeing something go behind a tree, for example, like seeing an animal run past behind a tree, completely disappear, and then come out the other side of the tree. So we see a dog run behind a tree or something like that. There's something in our mind that pieces that back together and says that's the same dog, even though there is no evidence to that. There's only a high likelihood that's the same dog. It could be that one dog runs behind the tree and an identical looking dog runs out from the other side of the tree. There's no reason, like there's no well, I mean there is a bit of a reason to say that that is the case, but like, we're piecing this stuff together. And these human mechanisms are the things that we use to make animation work. The things that we expect stuff that looks really similar to what it did like a 20th of a second ago is the same object. So we're looking at this as like the oldest that we see of this, that we have kind of current evidence still left over for, is that people were doing this in the 1800s. For some reason, both of these things are in 1887. So I think that there was a very concentrated development in animation around that era. And we know that because the film industry appeared around 1895, 1896, when the first cinemas were opened. 1896 or 97, I think. I had to read up on this stuff, by the way. But the oldest use of this we see is the zoetropes, but there is a possibility there are historical descriptions of things in ancient China around 1st century BC that may have been this same idea of technology created way back then. We don't have any physical evidence of that though, so it's hard to say. But this zoetrope is something that just spins, and as you're looking into it, you will occasionally see through these gaps in the outside, and what you see through these gaps are fleeting images of these little sculptures that are on the inside. They don't have to be sculptures, they can be paintings. And your mind will trick you into seeing these birds flying, because like each of the different images is like the wings flapping. This is one of the very first animations captured on film. Is not actually a film camera. This is a horse running along a track, and at multiple different positions on the track, spaced, a couple of meters apart, are different cameras. And those cameras were all set to go off when the horse ran past different areas. So they basically took a whole bunch of still photos. This is what they did in The Matrix, actually. They did that with cameras that were in a circle around things. And so what they could do then with these is take all of these photos and piece them back together. And what we see is a vision of movement, which is not necessarily movement. They're all separate still photos that are actually taken in different positions on a track, but we see it. So around 1895, when both camera and projection technology had been created, we were able to then create the film industry, because the 35mm film camera at the time was able to expose what is it, cellulose film to light, and it would take an imprint of the light that it saw, and we could do multiple of those per second. And then we invented projectors to shine light back through the negatives of those films. Oh, is it negative? I can't remember. Yeah, but shine light back through those to then project that on the screen. We have the beginnings of film, and the results are what we see today. We still have projection and things, but things are getting much, much more digital. So during graphics, we have learnt about this. We've learnt about drawing frames. We have our frame render loop that is running. This thing's running at like, I don't know, 10 a second or so, but we're going at like 100, well, not 100 times, 10 times, at least 10 times. Actually, we can go at 100 times that pace. We just don't have the physical monitors to support that kind of speed of frame rate, but we can go much higher frame rate than that if we want to. So what we're looking at is, if this horse is a 3D model, if it is made up of geometry, if it's made of vertices and triangles, how do we decide how much our geometry should change in between frames? So up until this point, we've been moving things around. So we've been moving our camera around with our mouse, and we've been deciding how far it moves based on how much the mouse moves. But what if we want more detailed animation than that? What if we want an object like this that changes its shape during its animation? What are we going to do about that? Because what we're going to want to do is that some of these verts are hardly moving. So like the tail and like maybe part of the shoulder and the hips and stuff aren't moving, but these hooves are moving a lot. So different parts of the model are moving much more than other parts of the model. So how are we going to decide which verts move and how much they move? And that's what we get with animation. So simplest way to think about this is doing this by hand, which is old school, which actually it's not that old. People are still doing it. But we look at the history of, say, Disney, or we look at the history of Studio Ghibli and Japanese animation and stuff like that. We see that frames are drawn. And what we do is we draw a whole lot of frames and we play them back one after the other. So this is like hand drawn, pencils and paper, paint on cells, again, cellulose sheets. So there's like, transparent sheets that we can use to do things. So if we were going to do this in graphics, the vertices are in a position in one frame and the vertices are in a different position in the next frame. The next frame, the vertices are in another position. So when you're drawing this by hand, it's something that you can do. This, I love it. This actual animation here, you can tell, is based on this one. So someone took this animation and did a process known as rotoscoping, where you take something that exists in the world and you just draw over it. So they drew over it with this cute cartoon horse. And that way they got a realistic running, a realistic gallop cycle for this horse, because they took it from a real horse. So I liked this because it was like a quote to this actual kind of very, very early first animation. Yeah, Jason's saying 100,000 cells to make a traditional animated film. So much respect to the people that make those, and the amount of time and effort it makes. If we were to try to do things that way in our current system of computer graphics, again, I bring you back to the idea that this animation may have in the scene, ballpark 100,000, 200,000 triangles. So ballpark is similar, ballpark 100,000 verts. That is significantly more work than drawing a frame if I have to move 100,000 verts around. We don't have to move all of them. And if we had 100,000 of them and we were going to move these individually, I definitely wouldn't move all 100,000 of them. But if you have a panning shot, you'd have to move them. So you'd have like, I mean, I guess 50,000 of them would just shift across. So we could just do a translate on them and stuff. It's like, okay, there are ways to do this, but how would we do this? Let's say the horse is currently the main thing we're looking at in the scene. We've got a full three-dimensional horse. So we're looking at 200k verts in this thing, and we want to make sure they all go to the right places. We're not going to move these by hand. That's too much, right? So there has to be a way of bulk editing these. We have to find a way to move a lot of them at once instead of moving each and every pixel to its new position and hoping we magically get that right and we still get this kind of smooth looking flow of it. So odds of us doing that very, very low. The amount of work, super high. So obviously we're not going to do that. First option that seems really kind of like has to be the most intuitive option. Vertices aren't alone, they're objects, right? So we've already, like, this is exactly, I was like, you can remember this from tutorial 4. We've done this already. We've taken multiple objects. We've even put them in a scene hierarchy so that we only need to worry about them local to other objects. So we can have something orbiting and then another thing orbiting that thing. And because of our scene hierarchy, the final position of the object that's orbiting the orbiting object is kind of done for us. So what we can do is we can take the objects that we've already created. So I can take something that has 100,000 vertices in it, but just have its transform linearly interpolated along a curve. So I can have something with a very, very complex number of verts and say, look, you're just one object. And if you're one object, I can lerp you along a curved thing, and then I've got this kind of animation. I've got this movement and animation, so that's really cool, right? And I can animate multi-part objects like that by saying that, say I model the arms separately from the body on a person, so I can have them walking and I can have their arms swinging separately because there's a transform in between those. There's like a kind of a joint in between them because one of them is lower on the hierarchy than the other piece, and so I can just change its rotation and then the arm moves. So yeah, we can definitely do animation like that. And that allows us to join multiple objects together and things. This works really well for vehicles. This works really well for things with rigid pieces and stuff like that. So, but I want to look at what the downsides are to this, because yes, I've already kind of gone, okay, this is a cool approach, we can do this. But the downsides to animating like this is now we have to separate objects based on which bits are going to move. So this is intuitive and works really nicely for, like, let's say I have a tank in a game and the tank has a turret on the top. These can be completely separate objects that aren't even connected. We just like make sure that people can't see that there's a gap between them or make them kind of interlock so that there isn't a gap. So the turret just rotates and it's anchored to a certain position on the tank. So when the tank moves, the turret moves with it and the turret turns, right? And that's pretty simple because when the turret turns, we don't expect it to really be connected to any other parts of the tank. So separate objects, and we'd model them separately. But when we start to get to things that are more organic, so let's say I'm not real and I'm a VTuber and I have my arms moving around and stuff like this, and I'm mapping this to an object. That would mean that every single part of me that can move is a completely separate piece. So an artist would have to separately model each knuckle in my fingers so that they could move separately from each other. And this whole hand would have like this incredibly intense scene hierarchy going on here. So the scene graph for this hand would be more complicated than the scene graph in like a scene or that tank that I was talking about, because we've got like wrist. The palm has, like, I don't know, maybe 3 pieces. Each finger has 3 pieces as well. And even then, it's not going to look that great either, because what these pieces are going to be is individual pieces. And so this joint here, when I turn it, it kind of stretches over the top and it compresses on the bottom and stuff like that. Like, it's not something that should be made up of separate pieces. So like I use this analogy here. We start to look like deconstructed action figures. Like, you know, like those plastic toys and stuff, and they have separate pieces. And then we're going to look like we've got separate pieces with these really weird hard joins between things. So it gets really complicated and stuff. And yes, computers could handle that level of scene graph, but could we handle that level of scene graph when we're animating this thing, when we're working with it and stuff? So it can get too busy. And so we have to be careful about doing our animation like this. But the big thing that makes this really difficult to use is how good is this method going to be for an organic creature? So if I animated something out of solid objects and I wanted, like, I don't know, a dinosaur or something, or a cat. You can tell why I'm thinking of a cat by the tail that is, like, in camera at the moment. She's just sitting on my lap. Yeah, if I wanted to animate something like chicken, I wouldn't want her fur to kind of morph smoothly between things and not have her legs just be completely separate objects to her body, or a head be separate from her body. Like, that would be really weird. And it wouldn't look right to us. So the system of just having completely separate objects, animating them individually to each other in a scene graph, does seem to make sense, right? And it does in a way make sense, but it doesn't look right for what we want to do. So this is where we get a system that has been in use for quite some time and is still used a lot in games, and that is skeletal animation. So this is in between possible solutions. So one solution is we move every single vertex, and so the surface of the model moves in this smooth way because we're moving every single vertex. The other thing is we move objects only. So this skeletal animation is an in-between solution where we have objects in a hierarchy and we have the skin around the entire model. And we'll use those objects to actually morph the skin. So the way this works is we're treating the mesh as the external skin. So we call them the skin and the bones, basically, in skeletal animation. This is why, like, you know, when we talk about getting different skins for characters in games, this is actually it's like the outer mesh, the outer surface is the skin. So we have the skin and bones. So the analogy is obviously here to organic creatures. The bones are not like, they're not like bones like ours. They're not like a stick with joints on the end. They're arbitrary positions. They're just an abstract point in space. So you can actually see all of the different bones on this character. Like, there's lines drawn between them, but each one of these is just its own transform. So it has its own X, Y, Z and just sits somewhere in space. So this is exactly like a scene graph. A scene graph is a series of transforms in a hierarchical organization. So we can have, usually it's like the hip joint, or the somewhere in the torso, but often it's the hip joint is the core, is the center of the character. And then each of the right and left hips will be offset from that, translated off the center, and we've got knee joints here, ankle joints, and then toes. So this is quite a simple character because there's not much going on. And then we've got shoulders, upper arm, elbow, lower arm, wrist, and then it gets complicated around the hands. So they actually wanted to go to the trouble of being able to animate individual fingers here, which is why there's so many transforms in the hands. So like I said, lots of pieces in the hands. We still might use lots of pieces in the hands, but now, instead of having each of these pieces be an individual object, like an actual just kind of cylinder with a skin color texture on it, this is an abstract object which is like the skeleton inside a human body. So there's rigid parts inside the human body, but the outer surface stretches around those parts. So you can't really see it here that clearly, but as these things bend, the mesh does not separate. It doesn't open gaps as the knee bends, but the surface mesh surrounding that knee just stretches around that motion. So what we're getting is an ability to animate using a limited number of pieces in a scene hierarchy. So we could have, like, say 20 to 30 bones in this. I mean, like, it gets complicated once you do hands, but we do them individually. So there's like 20, 30 bones in the hand. And we can animate this character, so we can put it into a pose like this by only moving these bones and not having to worry about all the hundreds of vertices that are involved here. Michael's saying those fingers are very detailed. I assume the fingers are detailed because at some point they wanted to get close to these. The other thing you could do is have detailed fingers if you're using motion capture data for this. So very, very similar to modeling. Animation can be built up from primitives, from primitive movements, as in that is us doing things like scale, rotate, translate, transforms, and then building an animation out of those. Or we can go the opposite direction, like photogrammetry. We can take real world and capture real world movement and put it onto the model. So a lot of games and films are using motion capture data. Andy Serkis, if you've heard of him, played Gollum and a bunch of other things. I think he's in the Venom movie as the symbiote at the moment. Has built an entire career about being in a mocap suit and being able to act motion so well that people want to use him as the mocapped person. It's very difficult though. Motion capture data tends to be similar to the photogrammetry data because it comes from the real world. It's dirty and it's not clean and digitally exact, and so it often takes a digital artist a long time to take the motion capture data and clean up all of the sort of like real world sensing noise in it so that you can actually use it in things. I always used to like laugh because like people I knew in VFX would always say it's like, yeah, we could use mocap, but that's not actually going to be less work than us just building these animations from scratch. So it's interesting. So yeah, if we have these bones inside the skin, well, they're not actually all inside the skin, but the bones along with the skin, we can do this kind of in-between animation. So some of the details. Every vertex is affected by some bones. So if, for example, I'm looking at this bone here in the lower arm, the lower arm bone is going to have no effect on any of the vertices here in the model. It's going to have a great deal of effect on the vertices here and a small amount of effect on the vertices as they go up here and down towards the hand. So what we're going to end up with is basically each bone in the skeleton that is rigged to the mesh, so this is the rigging I was talking about, is going to be rigged at a different weight to the vertices near it. And this is not based on distance, this is based on a decision on how much stuff should move. So, for example, if I have a shoulder bone and a metal piece of armor over the top, let's say I'm rigging like the Mandalorian for something, that rigid piece of armor will be mapped one-to-one to a single bone somewhere in it. So that way it moves exactly with it and it does not stretch or morph. The fabric, the leather underneath that armor piece will be mapped to multiple bones so that as the arm stretches and turns, the entire geometry of the leather underneath will actually stretch and warp as it moves. So we can have rigid pieces or non-rigid pieces depending on how much we weight things to the bones. So basically each vertex is going to have an array or something or a list in it. It's more going to be a list because we don't know how long it's going to be, of which bones it is attached to and how much influence it will take from each of those bones. So that way, when I move the lower arm bone and I move it up like this, there are several sections of this that are definitely one-to-one to that. They will take it that from the lower bone, 100%. But these other sections here will take less movement from the lower arm moving. And there's a hierarchy as well. So the lower arm can't move without the upper arm moving, that kind of thing. So when we have, say, the skin around the elbow, it will take partial flexing on camera. I'm gonna do it another way. Yeah! I have to do it this way. I'm gonna try not to flex. So this bone here might have its position here, and it's mapped to most of the verts here. But it will be partially mapped to my wrist, and my hand bone here, like there's plenty more bones in a human hand, but for animation we might only have one in the palm, is mapped partially to the skin here. So if we mapped partially to here and here, this skin takes influence from this bone and this bone, and then moves in between the two. So I'm going to need to show pictures and stuff of this, but basically when a bone moves, it changes whichever vertices are mapped to it. So if you have a one-to-one mapping, those things follow the transform of the bone exactly. If you have a partial mapping, they'll move partially based on that bone. And that's how we can get this bit of skin here, which moves a little bit when the palm tilts, but it also is tied a bit to this bone here as it moves around. So the more weight there is, the more the mesh follows the bone. So I've got this like really simple example here of two bones. So there's an A and a B, and there's part of the mesh that's attached to them. And these are attached at certain levels. So this here is B 1.0, so it's entirely connected to B. And this one is A 0.3 and B 0.7. So it's mostly B and a little bit A. You'll see this kind of thing, right? When we're talking about linear interpolating, we're talking about like influence based on control points. This is a similar concept. It's influence based on the bones, but the influence is not parametric, it's static based on what decisions have been made about these verts. So in our animation, B moves to B2. And when it moves to B2, it exerts its influence over the vertices that are near it, or any vertices that have B listed in their mapping, basically. And so these things will see that B has now moved to this position. This is a one-to-one, so it'll take exactly the same transform change that B had to move there. This is a 0.7 here and a 0.3 of A. A hasn't moved, so we say that this is only taking 0.7 of B, so it's a scaled down movement. This one here only has a tiny bit of influence from B, so it moves a tiny amount, but mostly it doesn't move because A didn't move. So that's that kind of thing where we would have different weighting in the animation for different vertices, and that allows the objects to then move in a way that can stretch the mesh without necessarily like destroying it or anything. So we've got to actually be careful with how we rig this, because if we rig these values outside of like a total of 1.0, we can get really weird things happening. Michael said, if someone touches your skin, it affects the surface of your skin, but doesn't necessarily move any bones. How is that modeled? That is modeled with great difficulty. That's how, that's as far as I'm going to go here. We do get, in a lot of animation, deformation through other means. So deformation through collision with other objects, deformation just through muscles. So I said I wasn't going to flex. But anyway, if you notice here, I'm not moving the lower arm bone. I am moving these fingers, but this little muscle here that controls the fingers is actually, like, you can see there's a ridge there, and then it kind of balls up there, and then it expands out to here. So it goes back and forth like that. There are entire digital systems for virtual muscles. And when we get to very, very complex animation, realistic animation for film, that stuff will all be calculated as well. But when we're talking about games, that'll largely be ignored because it's a minor detail that won't come up that often. So every vertex mapped to bones. I think I've talked about this already. Yeah. So when we get to rigging, rigging involves building the skeleton. So you would build a skeleton for an object, and the skeleton's not always going to be simple like it is for an organic creature. For an organic creature, you just go, this thing's already got a skeleton, so we'll just map things to roughly the same as the skeleton. So the spine can have a few joints in it, so to know that people can bend their backs. But this arm is easy. It's one piece, but it will flex at either end. So we can have our joints at either end. If we want to get really, really detailed, we can have multiple around each of these joints to control the way the skin moves and stuff like that. But if we want to be simple about it, we can say the big bones are single bones each. The little bones like the spine we'll subdivide to a certain point. But we can abstract a lot of this stuff away. Remember, these are not real bones. They're just positions in space we're going to use to animate things. Facial animation bones are really interesting, because that's a case where there are way more bones than there are in the human body. Like, the human body has got the top of the skull and the jaw. There's only 2 bones, but we have so much expression in our face that there's all these bones attached there for animation. There's bones attached to your eyes so that you can look around with your eyes. So these are, we're talking about animation bones, not organic bones. So you get this kind of thing. It's all hierarchically organized. It's organized exactly like a scene graph is organized. The bigger pieces that control the center of the movement, in a sense, are the top of the hierarchy, and things like the fingertips and stuff are way out on the leaves of the hierarchy. So, because the fingertip, where the finger ends up, is relative to the transform at the shoulder, the transform at the elbow, the transform at the wrist. So, it is lower in the hierarchy than all of those transforms, in a sense. Then what we can do is say that every time we move the bones or we change the pose of the entire skeleton, using the transforms there and how much weighting those transforms have over the mesh, that tells us exactly where the points on the mesh end up. And yes, we can move the mesh around to make it interesting. We can actually change the size and shape of the triangles in the mesh by doing this. So once we've got that system going, once we have the capability to deform a mesh based on the skeleton, so going back to, this is obviously an example of this. So this is the skeleton in a kind of a resting pose. They'll often call this a T-pose. The T-pose is usually like with the arms further out, but this is like a basic pose to just check the model's working. And then this is a pose that an animator has put together and said, okay, this is an actual position that this skeleton can be in, and we map the mesh to the skeleton. One cool thing that we could do with this actually is we can use this same skeleton for multiple different people in the game, and you can actually get away with sometimes using the same animation on different people, and just because they're slightly different size and shape, you're actually going to get away with it. Examples are nearly all class-based role-playing games where you have so many different race and class combinations. The animation for doing something like swinging a sword or something might be the same with different races. So long as their body proportions are reasonably similar, you'd get away with it. Like if you're doing something between like an orc and a human, you probably wouldn't have the same animation because they don't stand the same way and they don't exert strength the same way. But if you have like, I don't know, a human and a half elf or something like that, you'd be like, yeah, they're gonna roughly be the same. We'll get away with them being the same, you know. It depends on the quality of the game. Very high quality games will be like, no, every animation is really specific, and the animation is just as important as the colors of the characters in showing who they are and how they work. Okay, so we can use the object-based animation we're talking about. So we can use the hierarchical object-based thing. So we have made it so that we're not doing per vertex animation. We don't have to animate every single vert moving around the scene. We only have to do the skeleton. And a lot of the skeleton comes for free because if I move my shoulder, my arm moves with it. So I don't have to worry about the pieces lower in the hierarchy unless they're also doing something individual. So if I'm moving my arm and my fingers at the same time, then I'd have to animate the fingers locally, and I animate my arm there, and the fingers will get moved because of the hierarchy. So it's nice, it keeps models attached to themselves as opposed to having the fingers as separate pieces. Like the hierarchy holds them together. This is like kind of scene graph hierarchy, right? And now we've reduced the number of things that people have to deal with. So the animator's dealing 20-30 bones, not 500 vertices. 500's a real low number. 500's like this, like 15-year-old game maybe has 500 verts, but even probably has more than that in the face. But yeah, our animators now no longer have to deal with large numbers of things, and we can just add more detail to our characters while we keep the same bone structure. So the animators don't have to do both things at once. And also we could revise our model without having to revise our animations because the animations are in the bones, not the surface of the model itself. So there's lots of benefits of this skeletal animation system. So we've reached a certain point here. We've significantly reduced our animation workload in terms of the number of vertices that our animators have to work with, but we have not reduced the number of frames necessary. So if I'm going at 144 frames a second, I might still have to say For every single possible one of those 144 frames, these are the transforms that the bones are in. And we don't want to do that, right? We don't want to have that many transforms happening at once. So what we would be doing is we would be setting up poses for our character or our object or something like that, and say, okay, we're in this pose, and then we move into this other pose. And these might actually be very, very separate from each other in terms of time. And we call these keyframes. So we can have keyframes of just like, okay, you're in this pose, and then you go to this pose. So I can be in this pose, and then I go to this pose. They're pretty far apart. But because this is a series of transforms between bones, I can linearly interpolate between these two. So I can say, yeah, there's 300 frames in between this and this, but I actually only need this pose and this pose, and I can linearly interpolate the transforms over a certain amount of time between those two poses, and I'll probably get away with it. Like, we need to be a little bit careful of these keyframes, make sure that each one is defining an important point in the animation, but you can do this where each keyframe can be like seriously like 30-40 screen frames apart, and you'll still get away with this animation. And what we do is mostly the only thing that's changing is orientation of joints. So it's just a rotation matrix, and the rotation matrix can just numerically go between one and the next. And it's nice because the animators can think of this as just the angle of the joints. And this elbow joint only goes in this orientation, so it has a single value. It's just the number of degrees of rotation, and even that's limited. So this might be like 180 degrees down to like 20 degrees, and that's the entire range of motion, and you're never going to go outside of those numbers. So we've got an example here. This is from Learn OpenGL of poses here, and there is literally no animation information between these poses. So the only information that's been given is 4 poses, and in between them, we are just linearly interpolating the rotation of the joints in between those. There's a bit of scaling going on. I can see the legs are actually changing length. Or either that, or it's not scaling, but it's 3-dimensional. So as the legs are foreshortening as they go towards or away. So I find this really cool, right? Because like we've now taken away the burden on the animators for the number of verts they have to deal with. So they don't have to deal with however many verts we're going to add in for the quality of the object. We're also going to be adding in a lot of frames for the quality of the motion. They don't have to deal with that either. They can be like, look, we'll give you some keyframes, and we can write code that will interpolate between positions. So we know which pose we're up to in the animation based on how long the animation has run for. So this is going to be like, you know, 1/4 of a second for each pose. And so we go, cool, we can do 1/4 of a second for each pose. We use our delta time. We linearly interpolate between the poses, and then we get this smooth animation. So when we're doing this in OpenGL, what we're going to receive with our model is the animations and the bones and the weights. So we're going to get the rigging from the animators, or the riggers if it's separate people. And then what we would need to do is say that based on the bone weights in each vertex, we would take the positions of the bones and the offset that we are from the bone. So for example, this arm that I've been using as my example today, if I have a single bone in the center of it, all of the verts in this kind of weird cylinder, like with scaled parts of the cylinder, have a specific offset of how far away they are from that bone. And they have a specific offset. See, the ones here also have a specific offset for how far away they are from this bone. And so how much of each of those offsets we use for where this thing is depends on how much weight they take from each of those bones. So what we end up with is, based on the bones, the weights, and this kind of offset for where they should be, we always know exactly where each vert should be. So our job when we're doing this is we will take the bones and the bone structure and say, this is where that exists in the world. If we know where that exists in the world, then we use those weights and we calculate exactly where each vert should be. This is not that different from using a scene graph to figure out where something exists in the world. There's a reason why we teach you that first and I teach you this later, right? So then we know exactly where those positions are going to be. When we receive animations, they will give us keyframe information and timings. So they will say, this is how much time it takes between this keyframe and this keyframe. This is how much time it takes between this one and this one. So really detailed animations might be in milliseconds. I mean, they're all going to be in milliseconds, but some of them might be in hundreds of milliseconds in between keyframes. And so what we would do is, to play that animation, we would start the animation and we'd start a timer going. And we'd use our delta time each frame to say how far we've gone into this animation. And so if we're between two keyframes, and say we're like 30% of the way between two keyframes in time, so these keyframes are like 300 milliseconds apart, and we're 100 milliseconds in at that point, then we say we're taking 2/3, well, roughly, like 0.7 of this one and 0.3 of this keyframe. And so we've linearly interpolated between the transforms of this keyframe and the transforms of the next keyframe. So we can actually do that, where we actually like interpolate the values inside the transformation matrix. So we can figure out, based on the interpolated transforms, exactly where the bones would be at that point in time. If we know where the bones are using the weights and the offsets, we know exactly where the pixels, exactly where the verts are going to be. And then we punch that into all our shaders and our pipeline, and that fills out the pixels on our screen. So that's the process, right? So what we're going to have is the keyframes. Keyframes tell us where the bones are. Well, the keyframes tell us the transforms. The hierarchical transforms tell us where the bones are. Then we can tell from where the bones are. We use the weights to tell exactly where the verts are. And then we have our position for that frame. And then we punch that into our renderer, and our renderer goes off and deals with everything. So it's interesting, right? It feels like, and as I'm saying it, it feels like there's a lot of work here. But this actually all happens within our 144th of a second. We can do this. And the reason we can do this is because everything is like this kind of simple mathematics that we've worked on already. It's like everything is just transformation matrices. And if we have multiple transformation matrices, like the whole bone hierarchy, and then the weights of two different transforms, we can compose that all into a single transform and then apply that one transform to a series of verts. It gets a little more complicated because not all the verts have the same weightings, but we can do a lot of the calculation in the lead up and then just apply one transform to each vert, and then we'll get what we need. So that is animation, and that brings us to the end of this kind of segment that I want to talk about how art works in relation to computer graphics. So I hope this has been interesting, because it takes me out of my own comfort zone, in a sense, because I don't actually know how to implement a great deal of this stuff, because I'm not an artist. But I think it's really interesting to think about and to know about, because now we have some serious context about how we get the 3D models that we're going to be using. And starting today in our tutorials, we're actually going to import a 3D model made by someone else. So I think it was Simon who's been doing a lot of our tutorial writing. Just found a model that's not particularly licensed or anything, and we're going to look at the code necessary to import this model, and we're going to start using it in a scene. So stuff that we've covered is we looked at the entire pipeline, and we looked in detail a little bit at the 3D modeling and animation and rigging. So if you want to, you can actually try to do rigging and animation, but what I would say is take it easy if you're going to do this. We're not really set up for this at the moment. It's sort of beyond the scope of the course, but I did want to talk about it anyway because I think it's really interesting. And you know, so looking at the amount of work people put into the Flex channel on Discord for assignment 1, I'm sure there's people who are going to want to try to rig a model for the next assignment. So you can if you want to. It'll get you some bonus marks with a C. They're not worth any. I mean, like, actually they are this time because they're subjective marks. So you'll probably get a lot of subjective marks for doing stuff like that if you want to, but it's probably not worth the amount of time. But Try it. Can be interesting. Okay, I'm going to wrap it up there for today. I think we've just hit exactly, or just hit 12 exactly then. I will go into break mode, and I will come back and answer any questions people have. If people want me to go over the animation stuff in detail, because it's actually quite a lot of kind of layering on maths on top of itself, in a sense, to get that stuff going. All right, back in a sec. I'm still downloading. It might be a while. But you'll hear the music in the background. Jason was like, yes, please go over the maths. New haircut. It's not a new haircut. It's the same haircut if you're in lockdown for 3 months and then you just let it grow out. It's like, it's so long in the back. It's really funny. I am booked in for a haircut with my hairdresser, but I think it's in like a week. I think it is next week. So week 7, you will see me with an actual haircut. Simon's like, wish I had hair. Okay, so Jason said, yes, please go over the math. I don't know if I can go over all of the math. Jason, I can go over some of it. So I don't know where to start. First thing, build the skeleton. So the skeleton is going to be positions in a hierarchy. So transforms relative to each other. So the first transform's usually going to be the hip joint, which is considered most of the time in animations considered the easiest place to have the center of the model. So the center of the hip joint, then you build the legs out to the ground. But not necessarily the ground. You don't know where the ground is when you're making the model, but like 2 hips offset, so you translate them outwards to the side. That's their local transforms from the hip. The spine is also translations upwards from the hip. Usually when we're working with these, it's only translations and rotations. You don't generally want different scales in the bones of your model, because if you've got different scales, then everything affects them in different ways and it just goes a bit weird. So generally these are just positions in a model that are offsets and orientations from each other. So a lot of the time when animators are working with these, they don't necessarily call them bones, they'll often call them joints as well, because you can consider them as anchors for movement in a sense, which is what a joint is. And each one of them is actually going to be limited in how it moves to the others. Like your shoulder joint might be quite movable in a sense, like it can go in many different orientations, but it still can't go through the body, so there will be a limit in there's like a cone of movement that it can't reach. Having said that, you will see like elbows clip through torsos and stuff heaps in computer games, because they just sort of let it happen because it's not super important. whether that's perfect or not. But if you ever saw like an elbow clip through a torso in a movie, you'd just be like, what? Like, you know, like we're talking about the MCU and Marvel Cinematic Universe, they're pretty careful with their CG for those movies. And if you're going to make $1 billion on something, you can afford decent CG. They talk about the quality of CG in films being entirely based on how much money went into them. I mean, it's kind of like that. Like, everything we're talking about here, to make it look good, we're taking a lot of shortcuts to make it easy to work with. But if you want to, you can make it harder to work with so that the detail is better, and just put more money into it, which means you just pay people longer to make better quality animations and things like that. So the same way that we're looking at like keyframes, this is 4 poses that are very, very far apart in time and when linear interpolating. If we wanted really high quality animations, we can triple the number of poses, for example, and then we'll get better animation. So first thing we do is a skeleton with a series of transforms. We can build this up in the same way that we would build up a scene graph. So each one has a transform relative to its parent in the hierarchy, and if you go all the way up the hierarchy to the top, you will end up with a single transform based on the I should turn down the music a little. Genshin loading music in the background. I'm gonna see if I can actually get to this. Oh. No, I am not going to get to it. It hasn't finished patching. Oh well. I'll just pop out of that. You came back. Genshin has a habit of just popping stuff up like that. Anyway. So we can build up the transforms. We've seen how to do a transform hierarchy. The skeleton is no different from that. There will be some kind of structure in the skeleton in the animation that comes to us in the model that we are going to import. In terms of rigging, this is something that the artists will mostly do, but this is setting weights. So basically each vertex is going to have, actually I don't always know the implementation. Sometimes it's each bone has a list of vertices that it affects, and sometimes it's each vertex has a list of bones that affect it. It really depends on how your implementation is going to go about using these. But I don't actually know. There's probably a convention for either one of those directions, but I don't know which one it is. Part of me thinks that the best way to do it is each vertex says which bone it uses, because what you're going to do is you're going to loop through all the verts and try to figure out where they are. So you don't want to have to loop through the verts, then loop through all the bones to figure out which one affects it. If you loop through the verts and the information's there, then you go to the specific bones and you go, okay, what's your transform? And then I will use your transform to inform where I am. I think that would be the best way to do it. I don't know though. That's just me thinking that up on the spot. So, weights in the verts will tell us which bones to use to decide where the vertex is. Where the vertex is. And which bones it has to take its transform from. So it takes a percentage of transform from one, a percentage from another. In the same way that we're linear interpolating between two positions, we can linear interpolate between two transforms and end up in a position halfway between them. Halfway or partially, anywhere in between them. So we would, in the rigging, set up all the weights so that the mesh deforms gracefully and gradually in between the bones. So if I am a CG model, when I turn my elbow like this, no gaps appear here. So these verts are all still connected in triangles across. Oh, Jason's looking for example model animations and specific algorithm implementations and equations. I don't have any of that stuff here. I think if we want to go into that detail, hang on. I can show you where to look, because I think if we're going to go into this, it will take me hours. But here we have in Learn OpenGL the 2020 guest article here on skeletal animation. I took some stuff from here, but here's you get actual detail here, and there's way more detail than I can talk about now in like 10 minutes. But I think the best thing I can do is send you here, and then you can go over this in detail. So you can see the images that I took to put in some of the slides here. And this actually uses a particular model loading add-on program plugin. I don't know. That you can use to take certain models. Simon, I don't know if this is the one that we're actually using for our tutorials. But anyway, this will go through what I was talking about, but in great detail. There's a lot of stuff in this course where I'm not going to go through things in great detail because there's only so much time that we have, so I had enough time to devote a lecture. Oh, Sam's like, no, we're not using async. I haven't actually looked at this week's tutorial yet. I know some of it, but I haven't looked through it. Sam is Simon now. That's cool. Yeah, so we're talking about this hierarchy of objects. We're talking about keyframes, and there's also like the actual diagrams for how you will receive the information on the animation data. So since we're not using async, we're not getting exactly the same thing, but it's going to be theoretically like the same. So there's also some code here talking about how to take the influence of each of the bones over each vector to get its final position and things. So yeah, that's as much as I can give you here, because I think that like if I was going to go through it in detail, I mean, as it was, I spent like 45 minutes talking about animation, so that was like half of a lecture. That's about as much time as I can spend on it. But there's a whole bunch of stuff about how the actual code works and how the classes work to actually do this. You know, I think this would be your best bet. Go through this in detail if you want super detail on it. And this is even the stuff I was talking about. It's like, yeah, here's the keyframe that we're at and the next keyframe current time. If we're going to linearly interpolate in between them, we're going to look at the actual values for how far away are we from the last keyframe, how close we are to the next keyframe, linearly interpolate between those two and do that. Yeah, so there's, as you can tell, there's way more stuff than I have time to talk about here. But you can actually go through. They actually did this. That's an animation from World of Warcraft, by the looks of it. I don't know if they've used the same thing. But yeah, check that out. Hopefully that will give you that extra information that you're looking for. I obviously had to condense it. As you saw, I finished dead on 12. I was obviously condensing this information in. I haven't actually implemented all of this. I think it's like 4 or 5 years ago I implemented this once. So I don't remember at all. But I remember enough to be able to teach about it at least. Oh, we're using tiny obj. That makes sense. I've used that one before. But anyway, in your tutorials, you'll get a little bit more, but we're not going to go too deep. We're definitely not going to do rigging or skinned animation and stuff like that, because it's just so complex. But we're going to do animation of an imported model. All right. Any other questions? I'm just kind of assuming, since no one else has said anything, that we're kind of done with the post-lecture section of the lecture. It brings back to this thing. This was a fun little project to do. It actually was really easy. Just because at the time I was teaching in games stuff, so I could get licensed to Autodesk stuff because the place I was doing had all these licenses, so I could just use stuff like this. So it's pretty cool being able to just take a bunch of photos. I don't have the photos anymore, but it was actually a really simple set of photos. It was like I put this thing on a block of wood so that it would be level and just rotated it around, just took a whole series of photos. And it was enough to get this level of quality detail on an object. Granted, I would never want to just drop this into a game engine, considering how many triangles it has, but it's still interesting that it can pick up geometry data. It's not exact, and there's these weird gaps here. There's a gap in the top of the head, and it's usually based on just how many photos I took and at what angle. So there's bits missing and bits that aren't perfectly straight but are curved a bit like that, but still pretty good. Jason says it looks fun. I think the painting is a lot of fun. Getting all these little like metallic looking edges and stuff like that, like on this weapon, to get it kind of looking like it's reflecting light in interesting ways. It's interesting, and it's actually got a lot of crossover. So a friend of mine who's a professional digital artist looked at my stuff, and he said, all you need to do is a minimal amount of training and you could be a texture artist, no worries. Because you painting physical models, it's exactly the same thing. Like, the geometry already exists, and then we're painting things to match that geometry. You happen to do it in this kind of micro scale on these tiny little models. If you had like a drawing tablet and the texturing thing, your use of colors and stuff like that would be exactly what we'd want for something to be working in games and stuff. And it's like, oh, that's really cool. I haven't ever actually done it, but I think it'd be kind of fun to take models that someone else has made and just paint some textures and stuff. Someone saying, look for Genshin vids, click to this instead. Genshin's still in maintenance. So the entire 2 hours of the lecture, I was unable to actually show any Genshin, which is super sad, because like I thought that this would be like, because we're talking about animation, one of Genshin's strengths is its character animation. But I was unable to show it, because once every 6 weeks Genshin goes down for about 3 or 4 hours, and it happened to entirely encompass this lecture. I'm still a little frustrated about that, but you know, we'll live. Okay, I'm going to wrap it up there. Thank you all for coming along. I hope that the learning about the art pipeline and the technicalities of things like modeling and animation were interesting to you. And they've got a lot of context for the things that we're going to be using and making when we go on into lighting and stuff like that as well. All right, see you all. Reminder, no lectures next week, because it is week 6. It is our flexibility week. I may organize some kind of non-formal event, in a sense, which is just me streaming some games that I've talked about in this course, maybe, or something like that. But there's not going to be formal lectures. You don't have to turn up to anything next week. It's entirely optional. But I'll send out a notice about this at the end of the week. I realized that I forgot the week 5 notice, because I posted about the survey, and then I didn't post anything else about week 5. But for week 6, I will definitely post something to remind everyone that there's no lectures and tutorials. Okay. See you all in 2 weeks, or maybe in 1 week if I do something else. If I decide to do something else interesting to just kind of have some entertainment in the week off. All right. See you later.